In our last lesson, we learned Coulomb's law and the electric field due to point charges. We used the superposition principle to add up contributions from multiple charges. But real-world charges are rarely isolated points. A charged wire, a metal plate, a cloud of electrons, these are all continuous distributions of charge. Today, we'll learn how to find the electric field when charge is spread along a line, across a surface, or throughout a volume. There are three types of continuous charge distributions, and each one has its own charge density. First, line charge density, ρL. This describes charge spread along a thin wire or line. It's measured in coulombs per meter. The total charge on the line is the integral of ρL dl over the length of the line. Second, surface charge density, ρS. This describes charge spread across a flat or curved surface. It's measured in coulombs per square meter. The total charge is the integral of ρS ds over the surface. Third, volume charge density, ρV. This describes charge filling a three-dimensional region. It's measured in coulombs per cubic meter. The total charge is the integral of ρV dV over the volume. Now, to find the electric field from any of these distributions, we use a powerful idea. Treat each tiny piece of charge dq as a point charge. Write its contribution to the field using Coulomb's law. Then integrate over the entire distribution. This gives us three integral formulas. For a line charge, E equals the integral of ρL dl over 4 pi epsilon 0 r squared in the direction of AR. For a surface charge, replace ρL dl with ρS ds. And for a volume charge, replace it with ρV dV. These three formulas are the foundation for everything in this lesson. Let's apply the line charge formula to an important case. An infinite line of charge along the z-axis with uniform charge density ρL. We want the electric field at a point P located at perpendicular distance ρ from the z-axis. Consider a small element dl at position z' on the line. This element carries charge dq equals ρL dz prime. The vector r from this element to point P has two components, ρ in the radial direction and z minus z prime in the z direction. So r squared equals ρ squared plus z minus z prime squared. Now here's a key insight from symmetry. For every element at plus z prime, there's a matching element at minus z prime. Their radial components add up, but their z components cancel. So the total field has only a ρ component. To evaluate the integral, we use a trigonometric substitution. Let z prime equal minus ρ times tangent alpha. After working through the calculus, substituting, simplifying, and integrating from minus infinity to plus infinity, we arrive at a beautifully simple result. E equals ρL over 2 pi epsilon 0 ρ in the a ρ direction. This is worth memorizing. The electric field of an infinite line charge drops off as 1 over ρ, not 1 over ρ squared like a point charge, and the field points radially outward perpendicular to the wire. Now let's find the field due to an infinite sheet of charge in the xy plane with uniform surface charge density ρS. We want the field at point P located at height h above the sheet. Consider a small element ds at position ρ, phi, on the sheet. It carries charge dq equals ρS times ρ d ρ d phi. The vector r from ds to point P has a radial component minus a ρ and a vertical component h times az. Again, symmetry saves us. For every element at angle phi, there's one at phi plus pi. Their horizontal components cancel, only the z component survives, so we integrate only ez. setting up the integral in cylindrical coordinates and integrating rho from 0 to infinity and phi from 0 to 2 pi, we get E equals rho s over 2 epsilon 0 in the AZ direction. This result is remarkable. The electric field of an infinite sheet is constant. It doesn't depend on the distance from the sheet at all. Whether you're 1 centimeter or 1 kilometer away, the field strength is the same. For a parallel plate capacitor with equal and opposite charges, the fields add between the plates, giving E equals rho s over epsilon 0 and cancel outside. Let's work through an important example. A circular ring of radius a carries a uniform line charge rho L. The ring lies in the xy plane centered at the origin. We want the field at point P on the z-axis at height h. Each small element dl equals a d phi carries charge dq equals rho L times a d phi. The distance from any element to P is r equals the square root of a squared plus h squared. This is the same for every element on the ring, which makes the integration simpler. The vector r from an element to P has components minus a in the a rho direction and h in the az direction. By symmetry, the horizontal components cancel. For every element, there's one on the opposite side of the ring that cancels its radial contribution. Only the z component survives. Integrating around the ring from 0 to 2 pi, we get E equals rho L times A times H divided by 2 epsilon 0 times the quantity h squared plus a squared to the 3/2 power, all in the az direction. Two important checks. When h is much larger than a, the ring looks like a point charge, and indeed the formula reduces to q over 4 pi epsilon 0 h squared. And when h equals 0, at the center of the ring, the field is 0, as symmetry demands. Let's recap the three key results from today. An infinite line charge produces a field that drops off as 1 over rho. E equals rho L over 2 pi epsilon 0 rho. An infinite sheet of charge produces a constant field. E equals rho s over 2 epsilon 0. And a charged ring produces a field along its axis. E equals rho L at h over 2 epsilon 0 times h squared plus a squared to the 3/2. The common technique in all three: exploit symmetry to identify which components cancel, then integrate what remains. Next time, we'll introduce the electric flux density vector D, which simplifies how we handle materials and leads directly to Gauss's law.